Let's re-examine an example we did earlier where we went through and determined the complex wave amplitudes of the two transmission lines on either side of a two-port network, which consists simply of an impedance, a lumped impedance in series. And if you recall, we went through and applied boundary conditions, and we were able to solve for this circuit. This time, we're going to use a different method. We're going to use the accordion method. Now, there really aren't any special cases involved in this circuit, save the case that the load at this end is a match load, and that will simplify things to the extent that we can apply the accordion method. So I just want to show here's another way of solving this problem. Generally speaking, anytime we have a circuit, certainly a microwave circuit, there are many different methods, or several different methods that we could use to approach it. And all are, if they're all valid, then you're going to come up with the same exact answer. And sometimes students stress about trying to figure out which method they should use, or there's the right method. But again, they all give their same answer. And that's why I go through and try to demonstrate different methods on the exact same circuit, so you can see that the results you get are in fact the same. So the special case we have in this circuit is that the second transmission line is terminated in a matched load, a resistor that's numerically equal to the characteristic impedance. And because of that, then we can replace this whole structure with this equivalent circuit. And we know that equivalent circuit is simply, likewise, a resistor that's numerically equal to Z0, because we know the input impedance will be equal to this value regardless of the transmission line length for the special case of a matched load. So this is the equivalent circuit once we've replaced the transmission line, terminated transmission line on the right side. And so we can now combine these two impedances, since they're in series, together and form a new equivalent circuit where this is the equivalent to the two-port device and the transmission line that is terminated in a matched load. So all of that has been pushed up, crushed up into this equivalent circuit. Everything that was to the right of this port plane now has been included in this equivalent circuit. What has not been altered in this equivalent circuit replacement is everything now on the left side of the port plane. This transmission line is the same as it was, and so we can go through and analyze this equivalent circuit and find answers here that will be the answers for this particular section. So the first step in this analysis is to apply now a boundary condition here at the end of this transmission line. We evaluate the total voltage at the location of Z1 is equal to 0 here at the end, and we get this result. And again, this makes sense because V0 plus is the voltage of the plus wave at Z is equal to 0. V0 minus is the value of the minus wave at Z is equal to 0. The sum of the plus wave and the minus wave at that point, therefore, is the total voltage at this location. Z1 is equal to 0. Same thing for total current. We evaluate it from the telegrapher equations, and we get this result. So what's our boundary condition here? Well, we know that the ratio of this voltage to this current must be equal to the load impedance. Or more specifically, the boundary condition we can use says that the line impedance here at Z1 is equal to 0 must be equal to the load impedance attached to the end of the transmission line. That is our boundary condition. But of course, the line impedance function at Z1 is equal to 0 is simply the ratio of the total voltage to total current, which we calculated or determined on the previous page, and therefore we can insert those to get this result here. This result, which is the line impedance at Z1 is equal to 0, the ratio of V1 to I1, is equal to this load, which we know from our equivalent circuit is equal to the sum of the series impedance, ZSR plus Z0. Now note Z0, since it's a real line, transmission line, a lossless transmission line rather, that value Z0 is going to be real. The impedance, the series impedance is assumed to be complex, both a real and an imaginary part. So now we take this boundary condition expression and we solve for V01 minus in terms of V01 plus. Recall V01 plus is our independent variable. It's essentially the source that is creating the scattered waves. And so we can determine the complex wave amplitude of the first scattering wave, that reflecting off that first port there, by rearranging this and solving for this value. And when we do, we get this result. And so V01 minus is in terms of the independent variable, V01 plus essentially the source, and then has this modifier which is in terms only of the physical parameters of that circuit, the characteristic impedance Z0 and that series impedance. Divide through by V01 plus, we get this ratio, and this is typically how we will describe these results, the ratio of a scattered wave amplitude to a incident wave amplitude, and that ratio turns out to be this. Now, if you recall, this is exactly the same result as we had before when we found this value using our boundary condition. So we used a different technique, but we arrived at the same answer. The one thing we didn't do here was determine the value of V0 2 minus. That other wave scattering value wasn't determined, and that wasn't anywhere in the math, wasn't our boundary condition, and that allowed us to get this answer more directly without having to worry about simultaneous equations, two equations and two unknowns. Notice there's another boundary condition that we could have used there. We used one that was that the line impedance at the end of the transmission line must be equal to the impedance of the load attached to it, but the equivalent of that, and with respect to wave viewpoint, is that the reflection coefficient function, when evaluated in the line, must be equal to the value of gamma L. This is an intriguing boundary condition to use in this case, because what we're trying to find is the ratio of V0 minus to V0 plus. And of course the ratio of V0 minus to V0 plus is the value of gamma 0 by definition. It is the value of the reflection coefficient at Z is equal to 0. But of course Z is equal to 0, Z1 equal to 0, is the location at the end of the transmission line where the load is attached. So we could have just used this boundary condition. The reflection coefficient function evaluated at the end of the line must be equal to the load reflection coefficient. And in this case, the load would be that equivalent impedance, that Z in 1. So this is our load reflection coefficient, and again what we use is the equivalent impedance, the Z is the L1 I should say, which is the input impedance to the remainder of that circuit that we calculated. Recall that was simply the series impedance plus Z0. And so we insert that in there and do a little algebra and we get this result. This is our load reflection coefficient for that impedance that terminates our first transmission line. We say by boundary condition that this must be equal to the reflection coefficient function when evaluated at the end of the line where the load is, and that in this case is at the index Z1 is equal to 0. And of course then that is by definition the value of gamma 0. The reflection coefficient at Z is equal to 0 is gamma 0, and gamma 0 is the ratio of V0 minus to V0 plus. And so there you have it. There is our result that is very directly determined. We recognize that this is simply equal to Z0, which must be equal to gamma L. Gamma L we calculate from the equivalent impedance, and therefore we directly get the result. So this is a different way of applying boundary condition. Again, the first way we applied the impedance, line impedance at the end of the line must be equal to the impedance of the load attached to it that terminates it. Here we said that the reflection coefficient at the end of the line must be equal to the load reflection coefficient that terminates that line. And in that case we got the answer a little bit more quickly, and really is because this ratio that we're trying to find is directly the value of gamma 0. And so look for this boundary condition when you can apply it, and it might make things easier mathematically. Again, two different ways, we get exactly the same answer. Which is the right way to use? It's up to you. So we found our first answer, the ratio of V01 minus to V01 plus, Now what about this second answer, the ratio of V02 minus to V01 plus? What is the wave amplitude of the other scattered wave, the scattered wave on the second transmission line? Well, to be able to determine this, we now need to expand our accordion back up. We need to go through and take our circuit and pull it back out in a more physical way, and then take our result we just got and propagate it down to that next section. So how do we do that? There's a number of different ways, and I'm going to show you several of them. So one of the things we could do is determine the total voltage on the at Z1 is equal to 0 at the end of the first line. And also we know that the ratio of, again, V0 minus and V0 plus is equal to the reflection coefficient, load reflection, or the reflection coefficient value, gamma 0. So we combine those two expressions, and we can determine now the value of V1. This is the total voltage at the end of the first transmission line, V1 at Z1 is equal to 0. And we've written that now in terms of the independent wave amplitude, the incident wave amplitude of V01 plus, and additionally in terms of the reflection coefficient value, gamma 01. We know gamma 01 is equal to this. All right, that was what we found out previously. It's equal to the load reflection coefficient. And so we can take this and insert in here, and what we find now is the total voltage at the end of the first transmission line in terms of V01 plus. Again, this is our independent variable. We can't solve for it. And a term that depends on the physical structures in the circuit itself. So what we've done, again, is find the total voltage in terms of the incident wave complex amplitude. So we've expanded the circuit back out somewhat. Here we have the two-port device with the series impedance. Here we still have an equivalent circuit for the transmission line that's terminated in Z0. And so now our equivalent circuit has two impedances that are in series. We know the voltage here at this location. It's written in terms of the complex wave amplitude of the incident wave here, but still we know that voltage. And what we want to do is propagate this knowledge to the other side of the circuit. We want to propagate it down the circuit. We want to take this value to determine, for example, let's say the voltage here across this input impedance. Well, how would we take this voltage to determine that? Hopefully you can see it's easily done by applying a voltage division. So here is our voltage division expression. The voltage V1 times this is the voltage V2 in this voltage here across our input impedance for that second transmission line. Of course, we know what this value is in terms of V01 plus. It's this thing here. So we insert this and we get this, and then do a little algebraic simplification, and we get this result. This is the voltage right here in terms of the complex wave amplitude that describes the wave incident propagating down the line toward this first port. So we've taken that independent value, and we've not only determined V1 in terms of V01 plus, but now we've determined the second voltage in terms of V01 plus. So finally, we expand the circuit out the rest of the way. We're back to our original circuit. We know what V1 is now in terms of, again, the unknown, or the independent value, the incident wave amplitude there. So we know what this voltage is, and from that we determine this voltage. And now we're going to use that to determine this voltage, the total voltage V2 at the edge of this transmission line right here. So this is easily determined, obviously, from KVL, that this voltage at the edge of this line at Z2 is equal to 0, that voltage is equal to this V2N by KVL. They're the same thing. And so we can conclude directly that this voltage is equal to this result. Now we have this voltage in terms of the complex wave amplitude of the incident wave on the other side of this circuit. So we have one equation for a value on that second transmission line. We know what the total voltage is at one particular point on that transmission line. Normally we would say we need two equations, two values, the voltage at one place and the current at some other place, perhaps the same place or a different place, the reflection coefficient and the current, or some set of two different statements. So we'd have two equations to solve for the two unknown complex wave amplitudes, V0 plus and V0 minus. But in this case we don't need two equations because we already know what the other value of the wave amplitude is. V02 minus, V02 plus rather, if you recall, is equal to 0 because that second transmission line is terminated in a matched load. The only non-zero wave amplitude on that second transmission line is V02 minus. So we don't need two equations to find this one value. We just need one equation, and this is the equation. So now we can go through and solve for V02 minus. So the total voltage at the location Z2 is equal to 0 is simply equal to the minus wave voltage at Z1 is equal to 0 because the plus wave voltage, remember, is equal to 0. Total voltage is equal to the minus voltage only because the plus voltage is equal to 0. Well, this is the minus wave voltage evaluated at the location Z is equal to 0. We have a name for that. That is called V0 minus. Remember, V0 minus is simply the minus wave voltage evaluated at Z is equal to 0. That's what we've done here. We've taken the minus wave voltage and we evaluated Z is equal to 0. That actually should be Z2 there. That subscript should be Z2, not Z1. And that'll give us the value at V02 minus. We know what this voltage is. We just calculated on the previous page, and therefore we know that this wave amplitude is equal to this. We can divide through by V01 plus, or independent value in this analysis, and this gives us then the ratio of V02 minus to V01 plus. The complex wave amplitude of the second scattered wave to the complex wave amplitude of the single incident wave on that two-port structure. So this is that result, and if you go back and look what we got when we did boundary conditions exclusively to analyze the circuit in a previous section, you'll see that it's exactly the same result as we had before. So again, I want to emphasize there are many different ways of getting this answer. If you recall, what we did to get this second answer was determine the total voltage at the end of the first line and use KVL to determine then the voltage at the beginning of the second. Voltage division rather, to find the voltage at the beginning of the second. But we didn't have to do it that way. Again, we just need one equation to be able to solve for that second unknown wave amplitude, the V02 minus wave amplitude. And so we could have, instead of determining the voltage here at the beginning of the line, we could have determined the current at the beginning of the line. And we do that by simply using Ohm's law. We take the voltage from here to here, and we've calculated, again, in terms of V01 plus, and take that and divide by these two, the sum of these two impedances. And that would give us then the current that is flowing through them, and that would give us then this current I2N. So we take the total voltage solution that we had before. Instead of using the voltage division math that we used in the previous analysis, now we simply divide by the impedance using Ohm's law, and we get the value of I2N. Now here's kind of the tricky part. We know the value of I2N, and what we want to do is use that to determine the value of the current now at this end of the transmission line at Z2 is equal to 0. But remember, because the index is defined as increasing as we move toward this interface, a positive current is defined as one that is flowing toward the left. And so we look at our arrows, and again, this is why it's so critical that you write your arrows on your schematic, otherwise you can't possibly get the right answer or even be able to interpret the answer that you get. If we look at this, we see from KVL that I2 is not equal to I2N. I2 is equal to the opposite of I2N. There's a minus sign there because of KCL. And so we take the value that we calculated for I2N and we multiply by -1, and this then gives us the result, which is this transmission line current I2 here at the very edge of this transmission line. So now we use our telegrapher solution to evaluate this total current I2 at the location Z is equal to 0. Just insert that into your total current equation that you had for from telegraphers, and be careful to evaluate the complex exponentials. Again, in this case, we know that V02 plus is equal to 0. And therefore, we only have one term in the result, and that is the complex wave amplitude V02 minus. So that's the result of our total current at Z2 is equal to 0. And of course, we know what the total current at the total current I2 at Z is equal to 0 is. We just determined that on the previous page, and so we equate this and this together. We have one equation where we can solve now for this unknown wave amplitude, complex wave amplitude V02 minus, in terms of the independent variable V01 plus, the incident wave. And so we equate these two things and do a little algebra, and we get this result, the ratio of the amplitude, complex wave amplitude of the scattered wave divided by the complex wave amplitude of the single incident wave on our two-port structure, and we get this result. Again, this is the same result we just got 2 pages ago. All right, so we got there by different means. We tried something different. Instead of using the voltage and propagating it over to determine the voltage on the other side, we used the voltage and propagated it over to determine the current on the other side. Again, as long as we get one equation with one unknown on the other side, we can solve for our unknown value. And when we do, even though we used a different technique, we get exactly the same answer. Now, there's another method we could choose to get this result as well. If you recall, what we've done in the previous 2 methods was take the total voltage at the end of the first transmission line and propagate the voltage across to the other transmission line, once getting the voltage on the other side. In the second case, we propagated across to determine the current on the other side. But we didn't have to start with the voltage on the first transmission line. We could have used the total current at the end of the first transmission line. So we go back and look at the result we got from our first analysis, and instead of determine V1 at Z1 equal to 0, let's determine the total current I1 at Z is equal to 0. And we know from the telegrapher equation, we get this result for the total current when we evaluated Z is equal to 0. But now we can insert for 0,1 minus, we could insert this result in there. All right, in terms of V01 plus, and we get this, do a little algebraic manipulation, and we get this result. This is our total current at the end of our first transmission line in terms of the independent wave amplitude V01 plus, the incident wave amplitude. So now we're going to take this result for our total current at the end of this first transmission line and try to propagate that result across to the other side of the circuit to say something about the total current here at the edge of this second transmission line. Well, we look at these 2 currents and we know by KCL that they must be opposite each other. Again, this is not the function with respect to Z1. This is the function with respect to Z1 when evaluating at the specific value of Z1 equal to 0. The same thing for the second. So these are 2 numbers that we're equating, defining the current precisely right here to the current precisely right here. And by KCL, that's the relationship that we have. We know what this is. We just determined it on the previous page, so we insert that in there, and so we can rearrange and get this result. And so this is the ratio of V02 minus to V01 plus that we get, defining the wave amplitude in the second side. Same exact answer as what we had before. And so for completeness, we'll show one more method we could have used. Again, finding the total current on this side, we could use that to determine the total voltage on the other side, the voltage V2. And we use that with Ohm's law and KVL. Now I kind of compress this here to save space. If we had our equivalent circuit, the input impedance of this would be simply a 50 ohm resistor. And clearly then if we have this I1 times that goes through that 50 ohm resistor, and the resulting voltage across that input resistance of 50 ohms will be by KVL equal to V2. So we put the pieces together here, and this is the result. V2 is equal to I1 times Z0, Z0 being again the value of the input impedance for this structure, and by KVL that voltage must be equal to the total voltage V2. What is the total voltage V2? If we evaluate it for the telegrapher equation, it's simply this value. So this is equal to this. From KVL and Ohm's law, we get this result, and then we rearrange algebraically. And again, once again, we get the ratio of the scattered wave amplitude V02 minus divided by the complex wave amplitude of the single incident wave V01 plus. This is the result, exactly the same result as in the previous page, and the two other techniques that we used prior to that. We keep coming back to the same result over and over again, as we should, because each time we use the same, or we use valid procedures to get this to this result. So think about what we did here. In this example, we had an equivalent circuit that included simply at beginning the transmission line on the left side of the circuit, the first transmission line, and from that circuit we got one equation and one unknown, the unknown being V01 minus, and we were able to solve then for this result directly from that one equation. And then we took that result and were able to propagate it across the two-port device to the other transmission line, and there we got one value, and which led to one equation, which allowed us to determine this second result. One equation, one unknown, and we got the solution. And so we had a series of two single variable boundary equations to solve, and this is in contrast to the example we did prior with this circuit, where we used boundary conditions and didn't use equivalent circuits. There we came up with two equations and two unknowns and had to solve it. Now, it may not appear to be that simple to you that we solve two single variable equations to get the answers that we were seeking in this problem. It seems like we did a lot more math, but again, we were just doing solving the same problem over and over again using different methods. In fact, we went through, and there's really 6 different methods that we demonstrated here. All gave precisely the same results, and that's because they were all valid methods. And so this is what causes problems sometimes for students, really for any circuit evaluation, not just for microwave circuits, in that there are many different ways of going about to find the solution there. And because there are many different valid ways, sometimes I think it overwhelms the student with which one do I choose, how do I determine which one to choose. Again, the main thing to remember, as long as you choose a valid one, you will get the right answer. So in the going through the ways that we found the answers in this problem, for the first result, this is what we obtained, and we got that by using one of two different methods. So the first method was to apply the boundary condition associated with line impedance and equate that to our equivalent load impedance. And again, this is the input impedance of the remainder of the circuit there, the equivalent circuit. Or we could have gone through, and we did, apply a boundary condition with respect to reflection coefficient. Evaluate the reflection coefficient at the end of the first transmission line and equate that to the load reflection coefficient, again using the equivalent impedance that we calculated. Either way, we took the result and we determined then the total voltage at the end of that first transmission line, and that total voltage has to be in terms of this independent wave amplitude V01 plus. This incident wave essentially is the source that creates all the other currents and voltages, so it has to be in the solution that we derived. So either way, once we had the total voltage at the end of the first line, we went through and propagated that solution across to the other side. of the circuit. And so we did that using voltage division, and we got this result here. Actually, these are backwards. This should be V2 over here and V1 there, but anyway, the point is we use voltage division to propagate. Actually, it should be V1 to get V2, and we solve to get this result. Or we could have gone through and used the total voltage V1 and Ohm's law to determine the current on their side, I2. All right, we did both of these, and we solved for this ratio, and guess what? We got exactly the same result as before. Finally, the last two methods that we used, instead of finding the voltage at the end of the first transmission line, we determined the current at the end of the first transmission line, once again in terms of V01 plus, and then once we found that current I1, we could propagate it across to determine either the current I2 or the voltage V2. With the current, we found this result. Again, the same exact expression as before. And then here is where we took the current I1 and propagated it across the circuit by determining Ohm's law and KVL. We could find the voltage at the very edge of the next transmission line. And from that equation we solved, and we got the same result once again. So in summary, we used one of two boundary conditions for the determine that first solution, the boundary conditions either for the impedance or the reflection coefficient. And then once we determined that, we then used one of four different boundary conditions to propagate the answer across the series impedance to the other side. We boundary condition involving I1 and I2 using KCL, or I1 and V2 using KCL and Ohm's law. V1 and V2 using voltage division, or V2 and I1 again using Ohm's law and KCL. Any of those four gave you this exact response, or this exact equation rather. So why did I show you all those 6 different ways if they all conclude to have the same result in the end? Why didn't I just provide one and say this is good enough? Well, it's because when I deal with students in this class and they're trying to learn how to do this analysis, again, you can't go through and use sort of a recipe. You can't go through and use a template, a blue box equation. You have to go through and use your knowledge of electrical engineering, and there are many different paths that will get to the same answer. It's sort of like a crossword puzzle or a jigsaw puzzle. If I gave 2 identical puzzles to 2 different students and I said solve them, then the students would be able to probably solve each of them, but they would solve them in completely different ways. If we watched how they put the puzzle together, how they solved one word and then the next, it would be in a very different order. And that's the same thing with these analysis. Kind of think of these as puzzles, as brain teasers. You use what you have and what more knowledge that you have from your toolbox, and piece together a series of values that will lead you ultimately to the end. You can go through and just make it into a big algebra problem with boundary conditions and multiple equations and multiple unknowns. Oftentimes students will end up getting that answer wrong because there's just too much math to carry around and rewrite. And so again, I recommend that when you can, that you use this idea of an accordion, the idea of a equivalent circuit. Try to crush the circuit down into as simple a circuit as you possibly can, analyze that part of the circuit, and then propagate the answer from one part to the next, moving up the circuit as you expand and finally getting the complete answer.